Hi, this is Vamud from Sherbrooke, and this is our flight readiness review. But before getting started, let's meet the team. Hi, my name is Justin Breton, and this is my second year in electrical engineering. It's also my second year on the team. This year, I worked on onboard system development, and on the flight team, I will be payload operator.
Hi, my name is Vincent Paradis. This is my third year in mechanical engineering and my third year on the team. I act as mechanical designer and safety pilot, which I will be on the flight team.
Hi, my name is Jeanne Moorhead. It is my first year in mechanical engineering, and it is also my first year on the team. During the year, I worked as a mechanical designer, and on the flight team, I will be mission director.
Hi, my name is Caroline Pelletier. This is my first year in mechanical engineering, and it is also my first year on the team. This year, I worked as a mechanical designer, and on the flight team, I will be safety advisor.
Hello, my name is Thierry Leclerc, and it's my third year in electrical engineering, and it's also my third year on the team. This year is my second year as ground control station operator for the team on the flight line.
Hi, my name is Samuel Kenville. This is my third year in mechanical engineering, and it's also my third year in the team. This year I work as a mechanical designer, and on the flight team I will be mechanical lead.
Hi, my name is Alex Morin. It is my third year in computer engineering. It is also my third year on the team. This year I worked on the air delivery system, and on the flight line I'm going to be the imagery analyst.
My name is Jacques Cavilla. This is my second year in computer engineering, but also my second year with the team. During my first year I designed the communication relay, and during my second year I developed ground software system. On the flight line I will be chief image analyst.
My name is Mathis Gagnon. It's my first year in robotics engineering, and it's my first year on the team. This year I worked on automatic mission planning, and on the flight team I'll be the GCUS operator assistant.
Hi, my name is Mathis. This is my third year in electrical engineering and my third year in the group. I passed 2 years assembling PCBs for UAS. Most of the time on the flight line I'm the mission director. This year I'm the captain of the team.
This year's flight platform is our hexacopter Orion. It weighs 22 pounds and has a diameter of 43.3 inches. With the values taken from AUVSI 2018 competition, it has an autonomy of more than 30 minutes and about 4.97 miles at a speed of 19.4 knots. It has a thrust-to-weight ratio of 2.2. Orion's main components are the autopilot, the UGV, and the payload controller, which controls the gimbal, the camera, and the drop mechanism. Orions communicate to the ground control station using 4 different links. First, a 5.8 GHz omnidirectional antenna for the payload link. Second, a 2.4 GHz antenna for the pilot link. Third, a 900 MHz RFD 900 Plus for the telemetry. And third, a 915 MHz 3DR antenna for the UGV. All the ground control station computers are connected to the interrupt system. The payload computer receives the images and sends them to the imager clients. The GCS computer sends the telemetry to the interrupt system, and the imager clients tag the images and sends the target to the interrupt. All tasks will be attempted at the competition. We have high confidence in the autonomous task, the waypoint navigation, the stationary obstacle avoidance, as well as the object DLC characterization, geolocalization, and actionable tasks. However, we have medium confidence in the air delivery drop and drive to location task, since it has never been tested in competition. Many tests were executed throughout the year to ensure the platform is working as expected and to reduce the risk of crashing. These tests are separated in 3 different categories. First, the unit test, then the integration test, and lastly the simulations. The unit tests are where every subsystem is tested individually. Once they are working as expected and do not represent a danger for the UAS, they are integrated into the UAS. Integration tests ensure every subsystem are working together and do not interfere with each other. Lastly, simulations. Every system is tested in the air, running several practice flights. Once every system is working, full mission simulations are conducted.
For the autonomous flights, we started by testing and calibrating our autopilot. After, we tested the different systems on the drone, such as the ESCs and motors to see if they responded correctly to the commands given by the autopilot, the antennas to make sure they were reliable at least 2 kilometers at a speed of 64 kilobytes per second, the magnetometer and GPS to ensure it knows its position and attitude, and the fail-safes to make sure that in case of a failure of the drone, it remains safe for the surrounding people. Since all the systems worked perfectly on the ground, Orion was then tested in flight. During its first flights, the PID was adjusted to optimize the flight time and precision. Finally, since the drone flew perfectly well in manual modes, autonomous flight modes such as auto takeoff, auto land, and autonomous flights were tested without the payload to begin with and with the payload afterwards. Since then, the UAV conducted different autonomous flight operations, including 3 different competitions in full autonomous mode. Since the UAV hasn't changed from last year's competition, we are really confident of the accuracy of the waypoints. In fact, last year we had an average accuracy of about 3 feet, and we hope doing even better this year because our flight test shows we can go down to an average of 1.5 feet.
For the autonomous flight planning, first, we connect to the interrupt to retrieve mission details. We can see on the map the airdrop location and the obstacles. After, we create a flight plan that achieves waypoint, airdrop, and search area task. Lastly, we reroute the flight plan to avoid obstacles. Obstacles are avoided by creating waypoints around every obstacle at a safety range of 10 feet. The imagery system is composed of a 24-megapixel Sony Alpha A5100 camera as well as a custom-made 2-axis gimbal that is made to be small and lightweight. The imagery system has been tested several times in the air as it is also used for another competition. The payload link is connected to a 360 degrees tracking antenna that is used to transfer the images and command the payload controller. It achieved a data rate of 65 megabit per second at a range of 1 mile, which is more than twice the required bandwidth and more than the estimated distance that we will fly at the competition. Camera settings are set to optimize image clarity. Shutter speed is set to compensate vibration and aircraft speed. Rubber dampers are installed to reduce camera vibration, and we use a manual preset focus to avoid blurry images. We can use a fixed focus because the object DLC task is achieved at a fixed altitude of 170 feet. White balance and exposure compensation are adjusted to characterize targets more efficiently. With a 24-megapixel camera, it gives a 2 pixel per inch resolution at 170 feet of altitude, which is enough to identify targets. 0.4 Hz picture frequency at 19.4 knots of speed gives 50% image overlap to avoid missing any targets. Here are 2 images taken from last year's AUVSI competition. We can expect slightly better image clarity due to the new shutter speed setting and the new gimbal damping. To improve localization performance, 5 practice flights were made to calculate the time compensation needed between telemetry and image timestamps. Delays are needed to compensate for sensors, data transmission, and telemetry update frequency. During practice flights, 26 targets were located at an average accuracy of 7.7 feet. 2 competition simulation flights were conducted at an altitude of 164 feet. During the simulation, 8 out of 10 targets were located within 10 feet and 2 out of 10 targets were located within 20 feet. Location accuracy was calculated using a photogrammetry software Agisoft, which creates a map of the zone and calculated error in location of each images. Camera, telemetry, gimbal, and file transfer are all tested individually before installing them on the UAV. For example, manual and automatic camera trigger are tested as well as making sure that the telemetry matches the image's location. Integration tests are then conducted and systems are optimized to achieve a maximum score at the competition. For example, photogeolocation are optimized to compensate camera delays in sensors, tracking antenna positioning and offset is optimized to achieve a maximum data rate, and automatic camera and stop for search area is tested to make sure that the camera starts at the beginning of the search area and stops when exiting it. To ensure the payload operator is aware of the payload air controller state, live visual feedback is shown on the ground control station payload software Nexus command.
The automatic detection and classification of the image will be done in 4 steps. The table below outlines the different tools and manipulation used in each phase of the analysis. First step, we will find areas of interest in the image. If the operation is a success, we will find a shape in the letter area. Third, we will find a letter in the shape. And finally, we will find the color of the shape and the letter. This solution was developed preferring false negative to false positive.
We test the system by using past year competition image. In our test, the system was able to find every target. The hardest target to find was the yellow and orange star. Because we use TUSA algorithm for validation in phase 2 and 3, we can be sure that the system detects the good element. As you can see, we have some difficulty finding the yellow shape from the orange letter because the color similarity. But the system managed to do more than okay for this target, and because this is phase 4, we expect that the false positive will be removed.
This year, air delivery was a real challenge. To achieve with success this task, the team chose to use a winch combined with a custom release mechanism. This system allows us to drop gently the UGV while respecting the minimum altitude of 100 feet with the UAV. The UGV will transport the water bottle during all the mission. It will be delivered from the UAV by a 100 feet long winch. Once released on the ground, the UGV is able to move to a different target. The UGV is a complete custom design from the team. It is equipped with all the necessary components and telemetry to achieve the task. The UGV have a special design, giving us the opportunity to transport a water bottle while being the smallest. A two-wheels drive configuration was chosen to save on the number of motor and wheels to keep the weight as low as possible. Two small DC motors ensure the UGV motorization. They are capable of rotating at a speed of 90 RPM, giving a linear speed of about 1.85 feet by second. Finally, the UGV has an autonomy close to 22 minutes, which is more than enough to achieve its mission.
The UGV control system is built around a custom Atemega 328P based autopilot. It contains a 3-axis magnetometer, gyroscope, and accelerometer. There is also an altimeter and a GPS receiver for accurate localization of the UGV. A 915 MHz radio will allow for remote telemetry and disabling of the UGV in case of a problem. A dual H-bridge motor driver allows for a differential drive of the UGV. The theory of operation of the air delivery happens as follows. The UAV needs to take off and reach an altitude of 50 feet or more. Once this altitude is reached, the UGV is armed and ready for release. The UAV will then move to the required drop location and initiate the delivery. Once the UGV reaches an altitude of 25 feet, the UGV initiates a 45 seconds release countdown. This assures the UGV gets dropped if the altimeter gets wrong reading or if the winch gets stuck. The UGV will keep descending as close to the ground as possible. At an altitude of 6 feet or less, the UGV will initiate the release of the adapter plate. The UGV is now safely released and seeking its destination using GPS guidance. The adapter plate can now be wound up by the drop mechanism. The UAV is then able to leave the dropping location and continue its mission. We tried our air delivery system 20 times and got consistent results throughout our test. We had a 65% chance of reaching within a 5 feet radius of the target. Multiple outside conditions were used in our test which allow for accurate result. The team is confident the UGV will be delivered safely and precisely to the target.
Once every system was working individually, we started doing full mission simulations to ensure the team was ready for the competition. First, we did ground simulation, which include pre-flight preparation and post-flight processing with previous dataset. We also used flowchart and checklist. Once the ground mission simulations were made and the team was ready, we did full air simulations, which include a full mission sequence. To be able to achieve flight simulation, we had to set up an interrupt system with waypoints, airdrop location, as well as an off-axis target. We populated a search area with targets that we had to identify, and we did all the tasks required for the competition, including the UGV drop and drive to location, and the obstacle avoidance. Another very important part of our testing included the participation in another competition, which is Unmanned System Canada. At this competition, we had to do target location as well as target measurement and an air delivery, which is very similar to this year's AUVSI competition. We successfully achieved target location and measurement as well as the air delivery. After all the simulations and tests made, we were able to draft a table of our expected result for this year's competition. As you can see, we aim to play with our strengths, which are autonomous flight, stationary obstacle avoidance, waypoints navigation, as well as object DLC. we were able to approximate our overall result to about 80%. As you saw during the presentation, our systems are safe and ready for the competition, and we aim for top 5 this year. Thank you.